Bunsen burner.
A Bunsen burner, named after Robert Bunsen, is a common piece of laboratory equipment that produces a single open gas flame, which is used for heating, sterilization, and combustion. The gas can be natural gas or a liquefied petroleum gas, such as propane, butane, or a mixture of both.
History.
When the University of Heidelberg hired Robert Bunsen in 1852, the authorities promised to build him a new laboratory building. Heidelberg had just begun to install coal gas street lighting, so the new laboratory building was also supplied with gas. The laboratory required heating from the gas as well as illumination. For heating, it was desirable to maximize the temperature and minimize the luminosity. Previous laboratory lamps left much to be desired regarding economy and simplicity, as well as the quality of the flame for a burner lamp. While his building was still under construction late in 1854, Bunsen suggested certain design principles to the university's mechanic, Peter Desager, and asked him to construct a prototype. Similar principles had been used in an earlier burner designed by Michael Faraday as well as in a device patented in 1856 by the gas engineer W. Elsner. The Bunsen-Desager design succeeded in generating a hot, sootless, non-luminous flame by mixing the gas with air in a controlled fashion before combustion. Desager created slits for air at the bottom of the first cylindrical burner, the flame igniting at the top. By the time the building opened early in 1855, Desager had made 50 of the burners for Bunsen students. Bunsen published a description 2 years later, and many of his colleagues soon adopted the design. Bunsen burners are now used in laboratories all around the world.
Operation.
The device in use today safely burns a continuous stream of a flammable gas such as natural gas, which is principally methane, or a liquefied petroleum gas such as propane, butane, or a mixture of both. The hose barb is connected to a gas nozzle on the laboratory bench with rubber tubing. Most laboratory benches are equipped with multiple gas nozzles connected to a central gas source, as well as vacuum, nitrogen, and steam nozzles. The gas then flows up through the base through a small hole at the bottom of the barrel and is directed upward. There are open slots in the side of the tube bottom to admit air into the stream via the Venturi effect, and the gas burns at the top of the tube once ignited by a flame or spark. The most common methods of lighting the burner are using a match or a spark lighter. The amount of air mixed with the gas stream affects the completeness of the combustion reaction. Less air yields an incomplete and thus cooler reaction, while a gas stream well mixed with air provides oxygen in an equimolar amount and thus a complete and hotter reaction. The airflow can be controlled by opening or closing the slot openings at the base of the barrel, similar in function to the choke in a carburetor. If the collar at the bottom of the tube is adjusted so more air can mix with the gas before combustion, the flame will burn hotter, appearing blue as a result. If the holes are closed, the gas will only mix with ambient air at the point of combustion, that is, only after it has exited the tube at the top. This reduced mixing produces an incomplete reaction, producing a cooler but brighter yellow which is often called the safety flame, or luminous flame. The yellow flame is luminous due to small soot particles in the flame which are heated to incandescence. The yellow flame is considered dirty, because it leaves a layer of carbon on whatever it is heating. When the burner is regulated to produce a hot, blue flame it can be nearly invisible against some backgrounds. The hottest part of the flame is the tip of the inner flame, while the coolest is the whole inner flame. Increasing the amount of fuel gas flow through the tube by opening the needle valve will increase the size of the flame. However, unless the airflow is adjusted as well, the flame temperature will decrease because an increased amount of gas is now mixed with the same amount of air, starving the flame of oxygen. The burner will often be placed on a suitable heat-proof mat to protect the laboratory bench surface.
Variants.
Other burners based on the same principle exist. The most important alternatives to the Bunsen burner are Tekla burner. The lower part of its tube is conical, with a round screw nut below its base. The gap, set by the distance between the nut and the end of the tube, regulates the influx of the air in a way similar to the open slots of the Bunsen burner. The Tekla burner provides better mixing of air and fuel and can achieve higher flame temperatures than the Bunsen burner. Mecca burner, the lower part of its tube has more openings with larger total cross-section, admitting more air and facilitating better mixing of air and gas. The tube is wider and its top is covered with a wire grid. The grid separates the flame into an array of smaller flames with a common external envelope, and also prevents flashback to the bottom of the tube, which is a risk at high air-to-fuel ratios and limits the maximum rate of air intake in a conventional Bunsen burner. Flame temperatures of up to 1100 to 1200 DEGC, 2000 to 2200 DEGF, are achievable if properly used. The flame also burns without noise, unlike the Bunsen